This is going to video going over the first page of the answer key to projectiles launched at angles. That'll be problems 1 and 2. Number 1, a rock climber throws a small first aid kit to another climber who is higher up on the mountain. The initial velocity of the kit is 11 meters per second. You can see that as the hypotenuse here on my triangle. The angle is 65 degrees. That's the angle that is in the bottom left corner of that triangle. And if the other climber catches the kit at its highest point, how far above the first climber is he? Well, first things first, we're going to solve for the velocity in the x direction and the velocity in the y direction. So that's the two legs of this triangle. The x part of this triangle is the adjacent side, so I'm going to use cosine for that. And y is the opposite side, so we'll use sine. Right down here is where we solve for the velocity in the x and the initial velocity in the y. Velocity in the x is the adjacent, so cosine of 65 times the hypotenuse 11, giving us a velocity of 4.65 meters per second. And we plug that in here in our x direction. In the y direction, that's the opposite side, so sine of 65 times 11, giving us 9.97 meters per second, which is our initial velocity in the y. The rest of our numbers, final velocity is 0 because the problem says the other person catches it at the highest point. And at the highest point, it's going to stop going up, so the velocity final is 0. And the acceleration in the y direction for all projectiles is negative 9.8 meters per second squared. For this one, we actually have enough information in the y direction to solve straight away. We're going to be looking for the displacement, and we don't have time, so we're going to use the equation without time in it. That's our fourth kinematics equation, which is vf squared equals v naught squared plus 2ad. Rearranging this equation for d, we would subtract v naught squared over to the left and divide by 2a, which is what gets us this next step here. D equals vf squared minus v naught squared divided by 2a. Plugging in my numbers, 0 for vf, 9.97 for v naught, and a is negative 9.8. Plug all that into my calculator. Don't forget to square the v naught, and you'll get a height of 5.07 meters. Number 2, an arrow is shot 30 degrees above the horizontal. The 30 degrees is the angle in the bottom left corner of the triangle in the picture. Its velocity is 49 meters per second and hits the target. So the velocity initial is 49 meters per second. That's the hypotenuse of my triangle. What is the maximum height the arrow will attain? So I'm looking for that displacement in the y direction here at x in the picture. And also, how far away from the target is the arrow shot if the target is the same height as the shoot, or as the shot here. So here is the initial height, here's the target. So we're going to wonder basically what's the x distance from the arrow at the start to the target at the finish. First thing we need to do is find the initial velocity in the x and the y. Velocity in the x is the adjacent side, so we're going to use cosine of 30 to get that. And the y is the opposite side, so we'll be using sine. Right here, we found those velocities in the x and y initial. Velocity in the x is cosine of my angle, which is 30, times the hypotenuse, which is 49, which gets me a velocity in the x of 42.44 meters per second. Velocity in the y direction is the opposite side, so we're going to use sine of the angle, which is 30 degrees, times the hypotenuse, which is 49 meters per second, which gets us an initial velocity in the y direction of 24.5 meters per second. If we solve for maximum height first, we do have to do these two things separately because maximum height is one location in the path and the range position, or when it hits the target, is a different location, so we will have to do two different problems here. If we do max height first, the x velocity is 42.44. We solve that over here on the left. And now in the y direction, we have the initial velocity of 24.5. Maximum height means final velocity is 0, and acceleration is negative 9.8 meters per second squared. We can actually solve for displacement in one step. We have enough information to solve. We're going to use the equation without time in it. So vf squared equals v naught squared plus 2ad. Rearranging, just like we did above to solve for d, vf squared minus v naught squared, all divided by 2a. Plugging in our numbers, 24.5 for v naught, negative 9.8 for a, and vf is 0 again. Plug all that into our calculator, and we should get an answer of 30.63 meters for the maximum height the arrow attains. Our range position, or how far away the target is, instead of vf being 0, d is going to be 0. And we're going to be looking for displacement in the x direction because that's how far away the arrow is from the target at the start. Now here we do not have enough information to solve for that x distance in one step. We are going to have to use our y direction stuff in order to solve for time, and then use that time to solve for displacement in the x. D is 0, V naught 24.5, A is negative 9.8. We could actually, when using the third equation, which is that D equals V naught T plus 1/2 AT squared equation, we could rearrange that knowing that D is 0 and not have to use the quadratic formula. But I decided to do that since we are going to be using the quadratic formula a lot. That way I know that you're familiar with it. So when we rearrange that third equation, the D equals V naught T plus 1/2 AT squared equation for time, it's a quadratic. We would use a quadratic formula and it will look like this. And it'll look like this every time we have to use it. Negative V naught plus or minus square root of V naught squared plus 2AD all over the acceleration. I can plug in my numbers. So negative 24.5, because that's V naught, plus or minus square root 24.5 squared, plus 2 times the acceleration, which is negative 9.8, times d, which is 0, all divided by negative 9.8. That tells us that the time is either going to be 0 or 5 seconds. We know that the arrow is not going to teleport across the whole field that you're firing this thing at in no time at all, so 5 seconds must be the correct answer. We can plug back in to try to solve for d using our constant velocity equation of d equals v times t. So using all of our x values here, the displacement in the x equals the velocity in the x direction, 42.44, times the time, 5 seconds, to get 212.2 meters.